Hello everyone. We're going to be doing another past paper today with the 2019 paper 1, the multiple choice paper for higher physics. And yeah, we'll get cracking. It's only 45 minutes and it's multiple choice, so I wouldn't worry too much about this. It's pretty easy, all things considered. As you know, if you're stuck, you can just guess. Don't feel afraid of guessing. If you don't know the answer, guessing's always a good shot. But anyway, we'll get down into it. So this is lots of numbers that they might ask you to know. I think it's occasional that you get used to these. I definitely a couple times a paper, but you won't be expected to flip back here all the time. Alright, well, we'll get started with question 1. The graph shows how the speed v of a car varies with time t. The average speed of a car is during the 12 seconds is what? Well, average speed, right? So that's like adding up all the different speeds and then dividing it by a number of points. And we do actually have 2 points, so let's go and then just do that, right? So 15 plus 10, and then we only have 2, so we're just going to divide it by 2. So that's going to give us 25 over 2, which is, if I'm going to just make sure I'm not going nuts here, 12.5. Okay, well, and yeah, that's our answer. It's right there. Simple as that. You can also think of it as like, if you've got an average of this, like a linear graph, it's the exact middle there, right? It's you know, the like high stuff up here cancels out the low stuff down there, right? And also you can just have some common sense, right? If the lowest speed is achieved is 10 meters per second, it's not going to have a lower average than that, right? That's just nonsense. You can just eliminate all those. Overall, this is a fairly easy question. It's a nice start to the paper. A stone is thrown at 50 degrees to the horizontal with a speed of 15 meters per second. Okay, so this is going to involve equations that I don't think are in the relationship. We can check, but I don't think they put them in because they're just a bit mean and they decided that they just won't have them. Yeah, they won't have these equations in here, which is such a shame because, I mean, they have, because they're really useful. But I'll write them down on here. So basically all this is asking you to do is recall these equations. So sine is for the vertical component, and then for the horizontal component it's cos. So you will just have to remember these, but a trick you can do to remember this is that if you throw an object straight up, right, that's 90 degrees to the horizontal, all right, and then you would expect that its horizontal would be 0 meters per second because it's just going straight up, and then all of its it'll be 15 going up because you're just throwing it straight up. You're completely vertical. And if you go over here and you go, okay, well, if I do 15 times 90 cos, it's going to get me 0 because so that means cos must calculate horizontal. And then if I do the same thing with sine, we get 15. So sine is that. So yeah, I actually always forget which way around it is, and I use this method on my calculator just to make sure I'm fine. But what we can do here then is we can actually write down what the equation is. So I'm going to plug in our numbers. We have 15. So our base velocity. So that means 15 sine. And then for our angle, it's 50 degrees to the horizontal. And then for horizontal, it's the same thing, but with cos, same angle and everything. Okay, and then we can just look for this. So vertical components for 15 sine 50, I see 2 of them. Okay, so we've already narrowed it down to B and T. And then for horizontal, it's 15 cos 50. So that looks good. And I don't actually see, I do see that. And the only one that has both of them correct is B. Okay, right. Let's continue on. Moving on to 3. Golfer strikes a golf ball, which then moves off at an angle to the ground. The ball follows the path shown, which is standard parabola. The graph show how the horizontal component of the velocity VH and the vertical component of velocity VV of the ball vary with time t. As you can see here, there's a standard. We don't count air resistance and higher, so the ball's horizontal velocity is nothing slowing it down, so it just keeps chugging to 40 meters per second. This dip here is when it hits the ground. And same for, well, somewhat similar to for the vertical one. The only difference being is that gravity is doing a constant acceleration, so that means this drainage is constant, right? So it's a nice straight line because it's always pulling down as a solid 9.8. And then this uptick here, that's just because it hits the ground, it stops moving. Okay, what does it want to do? The speed of the ball just before it leaves the ground is what? Well, we have a horizontal, so maybe we should draw this out. So if I got a ball here, it's moving at 40 meters per second to this way, right? And then it's moving down at 30, or you can say it's moving up at minus 30, but this makes more sense. It doesn't really matter, so we'll see. Oh, look at that. That looks like a right angle triangle. Okay, so how about we use everyone's favorite formula, c equals a squared plus b squared, to solve this. So that means c will equal the root of a squared plus b squared. And I'll just run that through my calculator. So 30 squared plus 40 squared gives us 2500. And then we're going to square root that, and that gives us 50. So the resultant here is 50 meters per second. And there we go. That's our answer. Ooh, right. Now moving on to 4. A car accelerates from rest. Let's put it in. Excuse me. So that means the graph will start at 0 on a straight level road. The acceleration of the car is constant, which pair of displacement time and acceleration time graphs represent the velocity of the car. If we start with acceleration is constant, that means that this graph here will be a nice straight line because it won't change. It will be one continuous value. So that looks good. That doesn't. That looks good. That looks good. That doesn't. Okay, we've already limited 2 answers. So then I've seen from here that all these there's no velocity time graph, so we can't actually use this from rest part. But what we can do is that this is displacement. Displacement just means distance, right? So if you're accelerating at constant rates, you'll be getting farther and farther away, obviously, from your original target, but initial position. But you'll be getting each step will be further and further, because you'll be going. If you're accelerating, not accelerating at all here, you're just moving at constant velocity, you'll be going 10 meters away, then 20 meters away, and so on and so forth. So you get this nice straight line. But because we're accelerating, that means you start at 10 meters away, and it'll be going up to 22, and then it'll be going up to 36, and so on, so on. So the steps will be getting bigger. So that means you get this nice power function, right? Or this nice kind of curvish thing. So that means we can get rid of this line. And we're accelerating. We're not decelerating. So we don't want to level off. So that's garbage as well. So then it has to be A, because it's the only one that we haven't eliminated answers. Alrighty. Moving on to 5. 4 masses on a horizontal frictionless surface are linked together by strings P, Q, and R. Constant forces apply as shown. So we want to figure out the tension of the string. So if it's what string has the greatest and what string has the least. And so we can eliminate P the same P, Q, and R. These have got different masses, so they're not going to have the same tension. But how are we gonna get the tension? Well, you can actually ignore the strings when you're talking about one. If you measure one, you can just pretend that P itself is just towing a massive 70 kilogram weight, right? Doesn't matter that there's other strings in there, and R will only be towing a 40 kilogram weight. So P's got to be doing with R, and it makes sense, right? R's the last link in the train. It's only carrying 40 kilograms, but Q has to carry 10 kilograms and R and the weight. So of course it's going to have more tension, and it just increases as you go up the chain, which means P will have the greatest and R will have the least. Okay. A student makes the following statements about an elastic collision. Is it total momentum is conserved, total kinetic energy is conserved, or total energy is conserved? Which of these statements are correct? Well, start off, total energy conserved, that's always true, no matter what, usually. It's first law of thermodynamics, energy is conserved. You can't, matter or energy can't be created or destroyed. So, 3 is definitely true, 100%. Physics would break if it wasn't. Total momentum is conserved, that's another hard rule. Momentum is always conserved in an explosion or collision. So what about 2? Is total kinetic energy conserved? Well, it's an elastic collision, so it is. So the objects these are magical theoretical objects that they don't release any as heat or sound, so they just perfectly smash together and then perfectly come apart with the same energy as before. So total kinetic energy is conserved, which means the answer is E. Okay, we're moving down to 7. Terminal velocity Vt of a skydiver is given by the relationship, this horrific mess where m is the mass, g is the gravitational field strength, c is the gravity coefficient, p is the density of air, a is the area of the skydiver. 1 in 3/4, a skydiver of mass 95 has a drag coefficient of 1, and terminal velocity is 44, gravitational strength is 9.8, and density of air is 1.21. Area of the skydiver. So, annoyingly, we can't just plug on numbers and then get an answer. We're going to have to rearrange it. So I'm going to write down the original formula. Turn down my DPI. 2mg over PACD. Won't plug any numbers in it because that just makes it confusing as we start out. So what I'm going to do here is square both sides. If you square root, it undoes it. So Vt squared equals 2mg over PACD. Okay, so then what I want to do is we want to get A. So I'm going to times both sides by A because I'll undo. Because remember, this is getting divided by A, so we times it by A or undo it. So we'll go A Vt squared equals 2mg over PCD. And then all we need to do is divide both sides by Vt. I'll have an equation for A. Vt squared. Then we need to plug in our numbers. So we're running out of room here, but I'll write it down here, no one will notice. So that means A equals 2, what's the mass? Mass is 95 kilograms, remembering that. And then gravitational field strength is 9.8 because we're on Earth. P is the density of air, which is 1.21. And then, yeah, I'm regretting not moving this up here now. CD is the drag coefficient, which is nice and simple. It's just 1. And then, last but not least, Vt squared, which is 44 squared. So, we can actually just shove this into our calculator now. It's a wee bigger. Alright, I'll do it on my calculator. And remember to do brackets this time. The amount of mistakes I've been making on this. Yeah, you have to be kind of finicky with this, unfortunately. Times 1 times 44 squared, brackets. Boom, we get this rather long number, but if we round it to 2 decimal places, we get 0.79. And if we scroll back up to our original calculation, oh my god, that's B. Fantastic. Let's go on 8. Right here, and I'll go and erase some of this stuff. There we go. A spacecraft is traveling at a constant speed relative to a nearby planet. A technician on the spacecraft measures the length of the spacecraft as 275 meters. An observer on the planet measures the length of the spacecraft 125 meters. The speed of the spacecraft relative to the observer on the planet is what? Well, relative. That means we're going to have to use some relativity. So I'm going to put my data sheet and its length. So I'll zoom in. We want to use this equation here. L prime equals L root minus the speed. Okay, so write that down. Let's go and start plugging some numbers in. So the original, the non-prime L, will be what the astronauts measure. So the technician. So that'll be like the proper length, I assume. And then the observer would be what would be the lower one. Okay. So then we just need to find this root here. And I already know the speed of light. It's 3 times 10 to the 8. And I have to move my calculator out. Okay, so what are we going to do? Well, I'm going to actually go and start eliminating some of these options. Relativity of speed only happens at starts happening about 1/10 of the speed of light, so we can get rid of A, right? Because it's way too slow. It's only a couple kilometers per second. And E is faster than the speed of light, and D is actually the speed of light, which is not realistic for a spacecraft because it should be slightly slower because you're at the speed of light, which you can't accelerate matter up to the speed of light. So we know it's actually between B and C, but we do need to do the calculation to figure out for sure. So how am I going to do that? Well, I'm going to divide both sides by 275, so we get a fraction. Equals our root term. And then I'm going to square both sides. See, this will be a bit of a mess by the end, but oh well. And then I'm going to add 1 to both sides. I mean, take away 1 from both sides. And I'm going to times, and then next step, I'll times everything by -1. This will just make it a bit better. You see like later. So you have this minus term now. Fantastic. Times everything by -1. So that's +1 equals V over 3 times 10 to the 8. I'll see if I can actually perfect this 8. There we go. I'm going to move over here. Yeah, this is going to be a bit messy, ain't it? But what's a bit of maths without some mess every now and again? So I'm going to square root both sides. So we'll have a massive square root. +1 equals V over 3 times 10 to the 8. And then we just multiply that. So 3, this will be the last one, and then we shove it in our calculator. Times this huge root of minus 125 over 275 plus 1. And that's supposed to be squared, but okay, and that equals V. So let's go and calculate V now, and it's going to be a long one. Right, I'm going to go and throw this in my calculator. So 3 times 8, so it's 10 to the 8, so that's speed of light. And then we have to times it by brackets minus bracket 125 divided by 275, and then that is itself squared, and then we add 1, we do another bracket, and then we square root that, and what do we get? We get this horrific number, 267,217,62, and I've ignored the decimals, but look at that, 2.67, ain't that familiar? It's C. Right, that's it. There's a lot of maths there, but sometimes you have to do it. You pick high physics, what were you expecting, really? Let's go. 9. The redshift of a distant galaxy is 0.014. According to Hubble's law, the distance of the galaxy from Earth is what? Well, this is another time for our relationship table. So, down here, Z equals redshift, right? So, if you're looking at this, I know C is a constant, the speed of light. We know the redshift, so that means we can calculate V. And that means, using the Hubble constant, we can calculate D, which is... actually, I think he just wants us to calculate, and then we can calculate D, which is what we want. So, let's start writing this in. So, Z equals V over C, which means 0.014 equals some velocity of the speed of light. So, V equals the speed of light times 0.04. So, I'm just going to quickly do that. So that means the velocity is, if I'm working in scientific notation, that would be 4.2 times 10 to the 6. There we go. And then we can just use the Hubble constant. Hubble constant, we're going to have to scroll all the way up to our data sheet up here. Hubble constant is 2.3 times 10 to the negative 18. Okay, and then V equals Hubble constant OD, so 4.2 times 10 to the 6 equals 2.3 times 10 to the 18 times D, which means D equals 4.2 times 10 to the 6 divided by 2.3 times 10 to the minus 18. So I'm just going to quickly do that. And we get this horrific number, which I've just put into scientific notation as 1.82 to the 24. If we round up, that's 6. That would be B. 10. A student makes the following statements about the universe. The force due to gravity acts against the expansion of the universe. Measurements show the rate of expansion and the universe is increasing, and the mass of a galaxy can be estimated by the orbital speed of the stars within the galaxy. So, which of these statements are correct? Right, well, let's have a look at these all. So, gravity is fighting back against the expansion of the universe. That's why large objects like galaxies are running away from each other, but in between galaxies, the stars aren't running away from each other because gravity is holding the objects together. So I think 1 is correct. Measurements show the rate of expansion of the universe is increasing. That's also correct. We've been shown that it's increasing exponentially. The mass of the galaxy can be estimated by the orbital speeds of stars in the galaxy. Yep, that's how they found dark matter. Galaxies are spinning so fast that the gravity couldn't contain it. Of visible matter, so they had to find dark matter, right? And where you can do that is the mass of galaxy. If it's so, you have centrifugal force, right? So if you're rotating around something, it's gonna you're gonna have this like perpendicular force coming out. That's just kind of how rotation works. So that means if you're moving super fast, you've got to have, and you're staying like roughly the same, you have a constant force of gravity pulling you back in. So yeah, all these are correct, which means it's E. Nice and simple. Alrighty, an alpha particle is released in an electric field between metal plates P and Q. This is question 11. Alpha particle, remember, positively charged. Charge in the alpha particle is 3.2 times 10 to the negative 19 coulombs. The kinetic energy gained by the alpha particle while traveling from plate P to plate Q is 8.0 times 10 to the negative 16 joules. The potential difference across plate P and Q is, well, that's a lot of mouthful, but don't worry. In a relationship, we've got this handy dandy equation. W equals QV. W is work done, which is basically energy. So I'm just going to go and write that down there. And then Q is charge, because they ran out of letters in the alphabet. So it's 3.2 times 10 to the negative 19. And then velocity is what, well, not velocity, sorry, voltage is what we're trying to figure out. So if we just do some simple rearranging, we can divide both sides by 3.2 times 10 to the 19. So V will equal 8 divided by 3.2. Boom. And we get 2.5 times 10 to the 3. And we'll see you compare that. That looks like what we want. So the answer for that is D. Right, so number 12, an electron enters a region of uniform magnetic field as shown. So we got here. So this is region of magnetic field. It's kind of coming out of the page. It's towards you, right? Because that's what these dots mean. If it was into the page, it would be loads of X's. So we need to figure out the direction of the magnetic force on an electron immediately after entering the field. So this is what way the electron is going to move. What you do here, it's an electron. So we actually want to use the left-hand rule, or you can flip it over, or you can just use right-hand rule and do the opposite. So field's coming towards you, so your thumb will be facing towards your face. Your middle finger would be where the electron's going. Yeah, middle finger's charged. And then movement is your index finger. So that means that if you hold your hand up in front of you, that means it must be going towards the top of the page, i.e. A. Next up, we're going to 13, another statement 1. Student makes the following statements about the standard model. Every particle is an antiparticle. Alpha decay is evidence for the existence of the neutrino. The W boson is associated with the strong nuclear force. So afraid this is just going to be a lot of knowledge. Every particle has an antiparticle. That is true. There are particles like photons which don't appear to have antiparticles, but if you go into the details, they're technically their own antiparticles, so they do have antiparticles. Alpha decay is evidence for the existence of neutrino. Well, no, it's not. It's what it's trying to get it confused is beta decay is evidence for the existence of a neutrino, because it's where the neutron decays into an electron and a proton and a neutrino. So we can count that out. And then the W boson is associated with a strong nuclear force. Well, that's garbage as well, because if you remember your standard model, the bosons, the fourth medium particles, we have the supposed graviton for gravity, we have the photon for the electromagnetic force, strong nuclear force is the gluon, and the W boson is associated with the weak force. So 3 is garbage as well. So that means it has to just be 1. Okay, moving on to 14. A nucleus is represented by 22 francium 87. Decays by beta emission. So that means when you say beta, the atomic mass remains the same. Well, technically, it's slightly less, but it doesn't matter. So that when you go beta, you have a neutron, and it decays into a proton and an electron, neutrinos and whatnot. So that means that you gain an atomic number, because atomic number is the measure of how many protons are in the nucleus. So the symbol representing the nucleus formed as a result of this decay is what? So atomic number mass stays the same, so 23, is what we want. So we can get rid of all these. And then if we look at this, it starts at 87 and it's going to increase. So it's going to go up to 88. So it would be C. Moving on to 15 now, the diagram shows an experiment set up to investigate the photoelectric effect. The frequency of the incident radiation is varied and the current in the circuit is measured. Which graph shows the relationship between the current I in the circuit and the frequency F of the incident radiation? Okay, well, we can have a few look at this. Look at all these different graphs. And straight away, I'm already noticing what it's going to have to be it. It's going to have to be E. Why is that? Well, when you have a photoelectric play, everything has kind of metal has a work function. It's the minimum energy to eject electrons, which is the photoelectric effect, right? So we're looking for something that has a turn-on point, right? So if you don't have the minimum frequency, which is regarded as F naught, then it won't activate. But all these, they just go for all frequencies. A, D, B, C, it's all, they all work for all frequencies for whatever reason. But E, you see you have absolutely no current whatsoever. But then as soon as you hit the threshold frequency, it starts going up and up. And then when you increase frequency, you increase energy. So then there's more current because there's more electrons getting ejected. So yeah. Or because they have greater getting energy, so they're more likely to reach the other plate. Okay, so that's 15 done. I'll just circle, so yeah, it will be E. 16, a photon of energy 6.4 times 10 to the negative 19 joules is incident on a metal plate. This causes photoemission, i.e. electrons ejected, to take place. The work function of the metal is 4.2 times 10 to the negative 19 joules. The maximum speed of the photoelectron is what? Well, remember, the work function, that's the amount of energy required to get the electron off in the first place. So that means that the energy that we have to actually get the electron moving would be the total energy, which is this, minus 4.2 times 10 to the negative 19. So that would be 2.2 times 10 to the negative 19 joules of kinetic energy. And then we go EK equals 1/2 mv squared, 2.2 times 10 to the negative 19. Zoom a bit. And then, well, what's the mass of this? Well, it's an electron. So if we go all the way up here, it'll tell us the mass of the electron. Here we go, 9.11 times 10 to the minus 31. There we go. And then we don't know the velocity. So if you go and rearrange that, we basically just divide this number by these two numbers, and then we're going to square root it to get the velocity. Yeah, let's go and get cracking on that. So 2.2 divided by 0.5 times 9.11 equal that. That gives us this number, which is far too fast. As you can see, it's beyond the speed of light. But if we square root it, we get v equals 6.94, which is round up to 95, times 10 to the 5 meters per second. Oh, and would you look at that? That's one of our answers. It's C. Right, moving on to 17, and I've accidentally maximized my calculator. Right, 17, waves from two coherent sources, S1 and S2, produce an interference pattern, maximum detected position shown. Wavelength of the waves is 28 millimeters. For the third minimum p, the path difference is what? So we can actually write down our formula for this. And remember, it's a minimum, so it's actually going to be m take away a half. Lambda equals path difference. So that means that's 3 minus 1/2 times 28 equals path difference. And well, what's that? Pull out our calculator. 2.5 times 28 equals 70 millimeters, which is our answer. Number 18. A ray of monochromographic light passes from air into water. The wavelength of this light is 589 nanometers. The speed of this light in water is something. So I'm going to eliminate A and B straight away. They're far too slow to be the speed of light, and actually you can already calculate that 18 is C, because it can't be faster than the speed of light. It's going to be slower because it's going to a more optically dense medium, so you know it has to be C, but I'll go and work it out via calculation just in case. Because up here in our data sheet we can have refractive index is 1.33. Water. So if it's 1.33, then we can use our relationship sheet. So the angle, so n effectively equals v over v squared. So that means that air is always on top. So 3 times the 8 divided by v. If we go and rearrange this, we have 3 to the 8 divided by 1.33, and we get this. And if we round this, if we go and throw this into a thing, that's roughly 2.26 times 10 to the 8 meters per second, which is also our answer if you didn't work it out logically. So yeah, you don't even need to use the wavelength, that's just a red herring. When light passes through the outer layers of the sun, certain frequencies of light are absorbed by hydrogen atoms, producing dark lines in the spectrum. The diagram represents some of the energy levels for a hydrogen atom. The number of absorption lines in the spectrum caused by the transition of electrons between these electron energy levels is what? Well, this one, actually, we can do a ton of drawing for this. We just need to work out all the different lines. So from E4, you could go down to E3, E2, E1, or E0. Okay, so that's 4 so far. That's 4 so far, and then I'll go and see if we can erase this. Miss everything completely. Okay, and then if we go from E3, and then we go down to E1. From E3 you can go down to E2, or we can go down to E0. That would be another 3. That's fantastic. And then if we start from E2, we can go down to E1, and we can go down to E0, so that'd be 2. And then last but definitely least, E1 can only go down to E0, so on. And if we add up all these together, we get 10, which means the number of absorption lines caused by the transition of electrons between these energy levels is D, 10. Okay, moving down to 20. The output from an AC power supply is connected by an oscilloscope. The trace on the oscilloscope stream is as shown. The Y gain on the oscilloscope is 0.1 voltage per derivative. The RMS voltage of the power supply is what? Okay, well, 1 voltage per derivative, that means that whatever it's called, each of these boxes is 1 volt. So that means, well, the peak voltage there, that's 3 volts above the baseline, because you draw a line through there, that's what we're measuring from. And it will be minus 3 volts in the other way, but whatever. So V peak, if we go back here, I remember this formula for once, but there will be a V peak equals root 2 V RMS. So can throw that in. So we know the peak, but we want to figure out RMS. So we're going to divide 2 by root 2, see what we get. I mean 3 by root 2, if I actually remember what I was doing, because it's 3 is the peak voltage. And there we go. What do we get? Well, we get this horrific number, 2.12, and then continues on, probably, I think it's irrationally. But if we round up to, it only requires one decimal place, it's 2.1, which means the answer to the question 20 is A. Okay, the output from a single generator is connected to an oscilloscope. The trace observed on the oscilloscope screen is shown in the diagram. The frequencies from the signal is now doubled. Okay, the amplitude is unchanged. The Y gain setting on the oscilloscope is also unchanged. So that means that it will not change in height. We don't need to worry about that. The time-based setting on the oscilloscope is changed from 1 milliseconds per division to 0.5 milliseconds per division. Okay, well, this is another kind of logic one. So none of we can get rid of D. Amplitude's different, and we've already established that that's not the case. So if we increase the frequency, that means that you'd have twice as many peaks, right? So there's only 2 peaks there. So you'd think it would be A, but remember, time-based setting has been decreased, which means each of these boxes that are on this one would be 1 millisecond. Now they go for 0.5, which means you're viewing a smaller snapshot of the original thing, which means essentially this is the original signal if you didn't change the time-based setting, but you're zooming in on this bit because of your time-based setting, which means it will look exactly the same as the original because you've just zoomed in a bit, right? So the answer for that would be B. Right, number 22. A student sets up a circuit that measures the voltage across and the current in the resistor. The measurements and their uncertainties are as follows. Voltage 10 plus or minus 0.1 volts and current is 0.5 plus or minus 0.01 amps. So I'm going to convert these into percentage uncertainties, and then we'll pick the highest one and then apply it to the final answer. So 0.1 divided by 10 times 100, that equals 1%. Okay, cool. And then we'll do the same thing for current. What does that get us? Well, that gets us 2%. So we're going to pick the 2% one. So then we're going to have to actually run through the calculation. We use the mean answers. So V over I equals R. So that translates into 10 over 0.5 equals R, which is now 20 amps. Ohms. So what's 2% of 20? Well, we can calculate that out. That's 20 times 0.02. That's not 0.02, that's 0.05. That's 0.4. So it'll be plus or minus 0.4. And there we go. There's our answer. 23. A circuit is set up as shown. The power supply is negligible internal resistance. The power dissipated in the 3 ohm resistor is what? Well, I'm going to go over to our formula, and there will be a nice power thing. And power equals V squared over R. Well, we know R, V, so I'm going to write that down. We know R and we know V, so this seems like a winner. So just see 6 squared over 3, which is 9 over 3, so it'll be 3, but I'll just, so it'll be 36, it would be 9, but I'll just show that for you right now. 6 squared is 36, so you get 12. If my maths is awful, I don't know what's happening there. So you have 12 watts. And there we go. The answer to that is D, 12 watts. Yeah, remember, folks, trust your calculator more than your brain. It's, you know, made for this. Right. A student connects 4 identical light-emitting diodes, otherwise known as LEDs, to 2-volt DC supply as shown, which the LEDs PQ, RS, and will light. So remember, an LED is a diode, so it only lets electricity in through one way. So pin layout here, I always imagine the arrows are pointing in the opposite direction that the charges are flowing. So that means that be positive there and negative there. Okay, so we can just have a look down here and see if any of these matches up. Well, that's negative and that's positive there, and that's not lining up. So P won't light, but Q on the other hand, that seems like a winner. It's flipped around the correct way. But what are RS? Well, they're facing opposite directions, so no matter what, how much current it indicates, remember these are effectively one-way streets, right? So even if that you can go through one, you won't be able to go through the other because it's flipped around the opposite way. So R and S will never be able to light. So yeah, it will be only Q would the only thing be able to light. Everything else cannot. And we're on to the final question. A student makes the following statements about uncertainties. All measurements of physical qualities are reliable uncertainties. Random uncertainties occur when a measurement is repeated and slight variations occur. Systematic uncertainties in a quantity occur when measurements are either all small or larger than the true value quantity. Are these all true? All measurements of physical qualities are reliable uncertainties. Yes, there's no perfect measurement. You can't measure something perfectly. You always have a bit of leeway, either way, even of our best tools. Random uncertainties occur when a measurement is repeated and slight variations occur. Yes, yeah, in real life, even if you measure something with a meter stick or whatever, you're gonna align it maybe a bit weird. If you're gonna have slight variations, very slight, occur, and that's why you get random uncertainties. Systematic uncertainties, yeah, well that's when if I've completely messed up and I'm reading the wrong thing on the meter stick, that means it'll be systematic uncertainty. So it'll all be larger or smaller than the true value of the quantity because I've messed up, right? I'm holding the meter stick wrong. I've got it, instead of got it at 0, I've got it at 1 meter, right? So yeah, the total value is all these statements are correct. Should be E. And there you go. There's 2019 multiple choice physics paper. Tune in next year to when I finally complete the actual physics paper. But yeah, thanks for watching, folks. I'll see you all in the next one.